Welcome to Tungalalan classes. Today we are going to discuss the numericals of moving charges and magnetism. So out of that, the first numerical is they given that a circular coil wire is consisting of 100 number of turns. A circular coil is made with the wire which is having how many number of turns? 100 number of turns, and the radius of the circular current carrying coil will be is equal to what? 8 centimeter, and the amount of the current which is flowing through that given circular current carrying loop will be is equal to 0.40 amperes. So what they given? They given that a circular current carrying coil will be considered. In that circular current carrying coil, they are saying that it is consisting of 100 number of turns. It is consisting of 100 number of turns, and the radius of the loop is equal to 8 centimeter, and the amount of the current which is flowing through the coil will be is equal to how much? 0.40 ampere. 0.40 amperes. Then what they are asking? What is the magnetic field intensity? What is the magnetic field intensity at the center of the coil? So actually we discussed the application of the Ampere's law. So the circular current carrying coil will be considered at the center. The magnetic field intensity will be given by, the magnetic field intensity formula will be given by B is equal to mu naught Ni by 2R. B is equal to what? Mu naught Ni by 2R. So this is a formula for what? The magnetic field intensity. The magnetic field intensity at a point for the at a center of the circular current carrying loop. At the center of the circular current carrying loop, that formula is given by mu naught Ni by 2 into R. Now we substitute the values. First, what they given the data? They given that the number of turns is equal to 100 they mentioned. The number of turns is equal to how much they mentioned? N is equal to 100, and the radius of the loop is equal to, they given by 8 centimeter. That value is equal to 8 into 10 power minus 2 meter. That value is equal to what? 8 into 10 power minus 2 meter, and the amount of the current flowing through the coil is, the amount of the current which is flowing through the coil is equal to 0.4 ampere they given. So this is a given data. What they given? Number of turns given, radius given, and the current flowing through the circular coil also given. So you substitute all these values in the given equation of B is equal to mu naught Ni by 2R. You will get the answer. So what is the value of mu naught? Mu naught value is equal to 4 pi into 10 power minus 7. Mu naught value is equal to what? 4 pi into 10 power minus 7. Next, number of turns value is equal to 100. Number of turns value is equal to 100, and current value is equal to what? 0.4, and 2 means 2 only. Radius is equal to 8 into 10 power minus 2. Radius value is equal to what? 8 into 10 power minus 2. Simply we substitute the values in the given formula. B is equal to mu naught Ni by 2R. Now if you simplify that value, the answer is 3.14 into 10 power minus 4 Tesla. 3.14 into what? 10 power minus 4 Tesla. Tesla is the SI unit for the magnetic field induction. Tesla is a what? SI unit for the magnetic field induction. So this is about the numerical number 4.1. So the corresponding answer is equal to what? 3.14 into 10 power minus 4 Tesla. Now coming to the second numerical. In this second numerical, what they given that? They given a long straight wire which is carries a current of 35 amperes. Then what is the magnetic field intensity? At a point of 20 centimeter from the given wire. It is also nothing but the application of the either Bayes-Savart law or Ampere's law. So here I consider that a straight current carrying conducting wire. I consider what? A straight current carrying conducting wire at a distance of 20 centimeter. We consider a point. Distance R is equal to how much they mentioned? 20 centimeter they mentioned. Now I want to calculate the magnetic field intensity value. So already we know that according to the Eisenstein principle, when you consider the straight current carrying conducting wire, around the current carrying conducting wire, magnetic field will be developed, and the magnetic lines of forces are existed in the form of the concentric circular loops, So here, to find the magnetic field intensity at the point P due to the straight current carrying conductor, we have the formula B is equal to mu naught I by 2 pi r. B is equal to what? Mu naught I by 2 pi r. So whatever the formula we wrote on the board, that should be derived in the application of the Ampere circuit law. In the application of what? Ampere circuit law. So just simply they ask about the magnitude. Suppose if they ask the direction, how can we find the direction? We have to apply the right hand thumb rule. So the thumb should be present along the direction of the flow of the current, and the curling fingers will be giving the direction of the magnetic field. If you apply the right hand thumb rule at the point P, the field lines are passing into the plane of the paper. So here simply they ask what is the magnetic field intensity magnitude. If they ask about the direction also, we have to specify the direction the field is acting into the plane of the paper, Now coming to here, mu naught value is equal to how much? 4 pi into 10 power minus 7, and current value will be mentioned by 35 amperes, and 2 pi means 2 pi only, and R is equal to how much they mentioned? 20 centimeters they mentioned, that is nothing but 20 into 10 power minus 2. Now you simplify, this is a 2 pi 2 so this value is equal to 2 into 10 power minus 7 into 35 by 2 into 10 power minus 1. So 2 will be getting cancelled. So this 10 power minus 1 going to the numerator, it becomes to what? Plus 1. So the magnetic field intensity is equal to 35 into 10 power minus 6 Tesla. The magnetic field intensity value is equal to how much? 35 into 10 power minus 6 Tesla. This is the answer for the second numerical. Next, coming to the third numerical. So in this third numerical, they mentioned that again they consider a long straight wire that should be placed in the horizontal plane. So what is the difference between the last problem and this problem is, in the case of the last problem, they consider the straight carrying conductor which is placed vertically upwards. The field will be developed around the current carrying conductor in the form of a concentric circular loops. Now, whatever the straight conductor they assumed here, that a straight conductor will be placed in this case will be in the horizontal plane. How they will be placed the current carrying conductor in this case? They will be placed in the horizontal plane. Now, so that is carrying a current of 50 amperes. How much current is flowing through that given conducting wire? 50 ampere of current will be flowing through that wire, and they mentioned the direction here. The direction of flow of the current is from where to where? North to south direction. So here they specify the direction of the flow of the current. So from where to where? North to south direction. Then what they are asking? Give the magnitude and the direction of the magnetic field. At a point which is 2.5 meter east of the wire. So here we have to calculate both magnitude as well as direction. This type of numericals are somewhat difficult to find the direction. See here. Whenever they are asking north, south, east, west like this, whatever the problem, either it is a moving charges magnetism or in the case of the vectors in the first year. So first we have to make a plus symbol. And indicate the directions. So this is the east, west, north, and this is the south. So I specify the directions of east, west, north, south directions. Now, in this problem, what they mentioned, the direction of flow of the electrical current, is flowing from north to south. From where to where? North to south. So if current is flowing from north to south direction, at which point they are asking? They consider a point at a distance of 2.5 meters. They consider a point which is at a distance of small r is equal to 2.5 meters east of the wire. For that given wire, they consider the point P which is existing in the east side of the wire. So here north to south direction will be this, and current will be flowing in the vertically downward direction, and I consider the point P which is placed on the eastern side. Now, so this is a straight current carrying conductor. We consider the distance is small r. So to find the magnitude of the magnetic field intensity, already we wrote the formula in the previous problem. That formula is nothing but B is equal to mu naught I by 2 pi r. B is equal to what? Mu naught I by 2 pi r. So this is a formula for to find the magnitude of the magnetic field intensity for the long straight current carrying conductors. So first we will find the magnitude only. So here mu naught means what? 4 pi into 10 power minus 7. Mu naught value is equal to how much? 4 pi into 10 power minus 7. And the magnitude of the current will be given by 50 amperes. Magnitude of the current is equal to how much? 50 amperes. And 2 pi means 2 pi only. And distance value is equal to how much? 2.5. So that 2.5 I will be writing as 5 upon 2. Now, this pi will be getting cancelled. Pi will be getting cancelled. This 2 is also getting cancelled. 5 10 times. So what left here? 4, 10 power minus 7 and 10. So if you simplify this value, you will get 4 into 10 power minus Tesla. 4 into 10 power minus 6 Tesla. So this is giving what? Magnitude. So the magnitude of the magnetic field intensity is equal to how much we got? B is equal to 4 into 10 power minus 6. 4 into 10 power minus 6 Tesla. But they are also asking the direction of the magnetic field. They are also asking what? Direction of the magnetic field. Already I told, whenever they will be asking the direction of the magnetic field for a given long straight current carrying conductors, so which rule we have to follow? Right hand thumb rule. So what is the right hand thumb rule? The thumb is representing the direction of the flow of the current, whereas the curling fingers are indicating what? Curling fingers are indicating the direction of the magnetic field lines. If current is moving in the upward direction, the field lines will be acting into the plane of the paper. Already I explained in the last numerical. Because of here we have to calculate the direction. For that purpose only I explained in the last numerical. So whenever the current is flowing in the upward direction, the magnetic field lines will be acting into the plane of the paper. Now, see here, whenever the current will be flowing in the downward direction. So the direction of the magnetic field will be reverses. See here, whenever the current will be flowing in the vertically upward direction, the magnetic field will be acting into the plane of the paper. Whenever the current will be flowing in the upward direction, the field will be what? Acting into the plane of the paper. So here you just reverses the direction of the flow of the electrical current. As a result, as a result, the direction of the magnetic field is also changes. As a result, the direction of the magnetic field is also changes. Whenever it is moving in this direction, the field will be acting into the plane of the paper. So whenever the direction of the current will be reverses, the direction of the magnetic field is also changes. The direction of the magnetic field is also changes. The direction of the magnetic field will be acting out of the plane of the paper. Out of the plane of the paper, or the direction of the magnetic field will be acting, because we consider the horizontal plane. We consider what? Horizontal plane. See, this is indicating in this direction current is flowing north to south. So this is the eastern point. So at the eastern point, the direction of the magnetic field will be acting vertically upwards. Acting vertically upwards. So the direction of the magnetic field will be acting. Direction of the magnetic field will be acting vertically upwards. Vertically upwards. Simply you have to imagine current is flowing from north to south. Current is flowing from north to south. So you consider the point on the eastern side and you simply apply the right hand thumb rule. You will get the direction of the magnetic field will be acting vertically upward direction. So this is the problem number 3. The magnetic field intensity magnitude is equal to how much? 4 into 10 power minus 6 Tesla, and the direction will be what? Vertically upwards. This type of numericals are most important either in the CET or JEE. Okay. Coming to the next numerical. A horizontal overhead power line. Horizontal overhead power line carries a current of 90 amperes in east to west direction. So we consider what? A horizontal power head line will be carrying the current. So what amount of current it was carrying? 90 amperes of the current it was carrying. In which direction? East to west. East to west. Then what they are asking? What is the magnitude and the direction of the magnetic field? What is the magnitude and the direction of the magnetic field due to the current 1.5 meter below the power line. So same concept as that of the previous numerical. Now here they considered one horizontal power head. Horizontal power head line will be carrying the current. Suppose if you assume this is east to west and this is a north to south. So what they are asking, in the previous case they considered the point in the horizontal plane. Now how they consider? They consider a point P which is vertically below the current carrying conducting wire. So how they will be considered the point? They consider the point P which is placed just below the current carrying conducting wire. At that point what they are asking? To find the magnitude as well as the direction of the magnetic field intensity. See here, same concept. So this is, whenever they mentioned east, west, north and south direction, we have to form a plus symbol. And indicate the directions east, west, north, south directions. East, west, north, south direction. So the current is flowing from where to where? The current is flowing from east to west. The current is flowing from where to where? East to west. Now, how can we consider the point? We have to consider the point which is below of the power line. At what distance? I am assuming the distance of small r. Just below the power line. Now, to find the direction of the magnetic field, again we have to follow the right hand thumb rule. First we will calculate the magnitude of the field intensity. This is a straight current carrying conductor and this perpendicular distance is equal to what? Small r. Again the formula, the magnetic field intensity B is equal to mu naught I by 2 pi r only. So mu naught value is equal to what? 4 pi into 10 power minus 7. Mu naught value is equal to how much? 4 pi into 10 power minus 7. Current value is equal to what? 90 amperes. Current value is equal to how much? 90 amperes. 2 pi means 2 pi only, and the distance they mentioned that 1.5 meters. I will write 15 into 10 power minus 1. 15 into 10 power minus 1. Now if you simplify 2 pi 2 times and 15 6 ja. 15 6 ja. If you simplify this value, 6 2 ja 12. So 12 into 10 power minus 6 Tesla. 12 into 10 power minus 6 Tesla, which is giving the magnitude. So to calculate the magnitude, it's not an issue. So we know the direct formula B is equal to mu naught I by 2 pi r. B is equal to what? Mu naught I by 2 pi r. And by substituting all the values in the given numerical, you will get the required answer. But how can we find the direction of the magnetic field? See here. So I have to stretch my thumb in the direction of the flow of the current, So here, if you curl the fingers, the fingers will be directed towards south. If you curl the fingers, the fingers are going towards vertically downwards at the point P. So the direction of the magnetic field is acting towards south. So to get the direction of the magnetic field, simple imaginations. Whatever the current carrying conductor, according to your imagination, either you assumed in this direction or in this direction. Suppose I assume, so this point is what? East, and this point is what? West, and this point is what? North, and this point is what? South. So current is flowing in this direction. So this is the thumb, east to west. Now I curl my fingers. These curling fingers are acting in this direction. According to the previous assumption, this side will be indicating what? South. So that the curling fingers will be acting towards the direction of the south. So that the magnetic field is acting in which direction? Towards the south. This is about the numerical number 4. The answer is what? 12 into 10 power minus 6 Tesla is indicating the magnitude, and the direction of the magnetic field is equal to what? South. So while you are assuming the directions, be careful. So according to that, you will get the direction of the south. Okay. Next, coming to the next numerical 4.5. So here they are asking that what is the magnitude of the force? Per unit length on a wire, which is carrying a current of 8 amperes, and making an angle of 30 degrees. With the direction of the magnetic field, whose intensity is also mentioned, that is nothing but 0.15 Tesla. So here simply they considered a current carrying wire. In that current carrying wire, what they mentioned I is equal to 8 amperes of current will be flowing through the given current carrying conducting wire. How much current will be flowing? I is equal to what? 8 amperes will be flowing. And what they are asking that you find the force acting per unit length on the wire. You have to calculate, and they mentioned that amount of the current they mentioned. Next, it is making an angle of theta is equal to 30 degrees with the direction of the given magnetic field, and also they mentioned the magnitude of the field intensity is equal to 0.15 Tesla. 0.15 Tesla. This is the given information. What they mentioned, amount of the current is mentioned, as well as the angle made by the conducting wire with the direction of the magnetic field is also mentioned, and they also given the magnitude of the field intensity, which is equal to how much? B is equal to 0.15 Tesla. Now, what we have to calculate? Force acting per unit length we have to calculate. Already we explained the concept that, already we derived the formula also. If you consider a current carrying conducting wire, which is placed in the uniform magnetic field, so then the current carrying conductor will be experiences some external force due to the magnetic field, So here they mentioned that the current carrying conductor is making an angle of theta, with the direction of the magnetic field. So what is the general expression for the force? F is equal to, we know, Bill sin theta. F is equal to what we know the formula? Bill sin theta. So this is a formula for whenever a current carrying conducting wire is placed in the uniform magnetic field, so the expression for the force experienced by the given conductor, the required formula is what? F is equal to Bill sin theta. Now we substitute the values. B is equal to how much? 0.15. I will write as 15 into 10 power minus 2. 15 into 10 power minus 2, and current value they mentioned by 8 amperes. Current value is equal to what? 8. And length. So length value they didn't mention. Length means L only we will keep, and sin 30. Actually what they are asking, they did not ask the total force acting the entire length of the wire. They will be asking what? Force per unit length. So this length will be bring to the denominator part. So F by L is equal to 15 into 10 power minus 2, and this is 8, and this is what? 1 by 2. So this value is equal to how much? 8, and sin 30 is equal to what? 1 by 2. If you simplify this value, so this is what? 2 4s, 15 4s is equal to what? 60. So F by L is equal to what? 60 into 10 power minus 2, that value is equal to what? 0.6. Here it is nothing but force per unit length. So the SI unit becomes Newton per meter. So the required answer is what? Force acting per unit length along the length of the conducting wire. Unit length along the conducting wire is equal to what? F by L is equal to 0.6 Newton per meter. So this is the answer of the problem number 4.5. Coming to the problem number 4.6, it is application of this solenoid. See here. A 3.0 centimeter wire, carrying a current of 10 amperes. So they mentioned one straight wire. One straight wire whose length is equal to how much? 3.0 centimeter, and which is carrying a current of 10 amperes. Is placed inside the solenoid. Inside the solenoid. So, and how it was placed? The current carrying conducting wire is placed inside the solenoid, and moreover, it is perpendicular to the axis of the solenoid. Then, the magnetic field inside the solenoid is also mentioned by 0.27 Tesla. Then what they are asking, what is the magnetic force acting on the wire? Now, coming to the basic of the solenoid. What is a solenoid? A solenoid is nothing but if a long wire is bent in the form of so many number of turns, and the corresponding shape will be like a spiral spring, spiral spring. Such type of arrangement we are calling as a what? Solenoid. So this is indicating what? Axis of the solenoid. So it is indicating what? Axis of the solenoid. So we know that inside the solenoid at any point the magnetic field intensity will be remain same. The magnetic field intensity will be remain same, and the direction of the magnetic field, the direction of the magnetic field for the given solenoid will be the direction of the solenoid, the direction of the magnetic field for the given solenoid will be always acting along its axis only. So what point here we have to remember? In the case of the solenoid, in the case of the solenoid, the direction of the magnetic field, the direction of the magnetic field is always acting along its axis, is always acting along its axis. So that point we have to remember. Now according to the given problem, what they was saying that they consider a straight current carrying conducting wire which is placed inside the solenoid, which is placed inside the solenoid and which is perpendicular to the axis of the solenoid. So I am assuming that, so here AB is indicating a current carrying conducting wire. AB is indicating what? A current carrying conducting wire whose length will be perpendicular to the direction of the magnetic field, perpendicular to the direction of the magnetic field. Like that we have to arrange, a given current carrying conductor inside the solenoid. How can we arrange the current carrying conductor inside the solenoid? Means the current carrying conductor will be arranged perpendicular to the direction of the magnetic field, perpendicular to the direction of the magnetic field. Then what they are asking, find the force acting on the conducting wire, force acting on the conducting wire. So whenever these two will be perpendicular to each other, the angle between these two is equal to how much? 90 degrees. The angle between those two is equal to how much? 90 degrees. Now already we know that the force experienced by any one of the current carrying conducting wire, which is placed in the uniform magnetic field, is given by F is equal to Bill sin theta. F is equal to what? Bill sin theta. So here theta value is equal to how much here? Theta is nothing but 90 degrees since the wire is perpendicular to the direction of the magnetic field. Now simply substitute the values. What are the values they given? The magnetic field intensity value will be given by 0.27 Tesla, 0.27 Tesla, and the current passing through the wire is nothing but 10 amperes. I value is equal to how much? 10 amperes, and the length of the wire is equal to what? 3 centimeter. That is nothing but 3 into 10 power minus 2 sin theta means sin 90. So this value 0.27 into 10 into 3 into 10 power minus 2 sin 90 value is equal to how much? Sin 90 value is equal to 1. If you simplify these values, you will get 8.1 into 10 power minus 2 Newton. So what answer you will get? If you simplify the values, you will get the final result is 8.1 into 10 power minus 2 Newton. This is about the numerical number 4.6.